This is Math 456, computational complexity, and this is the third talk on finite automata. So let's just recall a couple of things. So we have an alphabet, sigma, which is just some finite set of elements. The most common is just the two-element set consisting of 0, 1. A word in the alphabet is a finite sequence of symbols, or if you want to call the elements of the alphabet letters, finite sequence of letters. For example, if the alphabet is just 0 and 1, then some words are 0, 0, 1, 0, 0, 1, 1, 0, 1, just one. The empty word, nothing in it. Those are words. And a language is a set of words in sigma. So it's not necessarily, and usually not all words in sigma. It's just some set of words in sigma. For example, if you take the English alphabet, not every concatenation of letters is a word. X, 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 Y, W is a string of letters, but it's not a word. You won't find it in the dictionary. A language is a set of words in sigma. And what we are interested in computational complexity are what are called regular language. A language L is regular if there is a finite automaton M such that L is exactly the set of words accepted by the finite automaton M. And so there are two natural problems. Problem one, given a DFA, deterministic finite autonoma, find its regular language. That means find all words W that M accepts. And problem two is the converse problem. Given a language L, determine if L is a regular language. That means, does there exist, or can you construct a finite automata M whose regular language is L. So given a set of words, does there exist a finite automaton M so that the set of words that the automaton accepts, and you know by now what that means, the set of words the automaton accepts is exactly the words in the language L. So a lot of effort in complexity, or in the complexity theory of finite automata, is to try to determine what are all the regular languages. And there are certain what are called regular operations that construct new regular languages from old ones. There are three regular operations, and the first is union. So if A and B are regular languages over the alphabet sigma, then now A and B are sets of words. So when you have two sets, you can take their union. So then A union B is a regular language. So the set of regular languages is closed under taking unions. I'm going to prove that in this talk. Another regular operation is concatenation. If A and B are regular languages, then A circle B is the concatenation of the languages A and B. So A and B consist of words. And what is in the concatenation of A and B is all words where the first letters are a word little a in the language A, and the remaining letters are a word in the language B, A and A, and B and B. So for example, if A were a binary word 01101, and B were the word 1011, then the word AB, the concatenation, would just be what you get by putting these two together. 01101 1011. That's the concatenation of these two words. And the third regular operation is called the star operation. So the star operation starts with one regular language. If A is a regular language, then A star consists of all words that you can get by concatenating a finite number of words in A. X1 in A, X2 in A, XK in A, for all K. Right? So this is the concatenation of words in A. So there are three theorems. The first theorem says the union of two regular languages is a regular language. The second theorem says the concatenation of two regular languages is a regular language. And the third theorem says the star of a regular language is a regular language. So it's the first theorem that I'm going to prove right now. And the second two require a little bit more work. Let me state this as a theorem if A and B are regular languages, then A union B is a regular language. So let's think about what it means for A and B to be regular languages. So proof. A regular language, implies there is a finite automaton M1, say M1, what is the 5 tuple for M1? There's a set of states Q1, an alphabet sigma, a transition function delta 1, a start state, which let me call R1, and some final states F1. So this is a discrete finite automaton, and the words it accepts are exactly the words in A. So M1 accepts the word W1 if and only if W1 is in the language A. And similarly, B is a regular language. So that implies, again, there exists, this backwards E is mathematical notation for there exists a discrete finite automaton M2. Say M2 has some set of states Q2, the same alphabet, transition function delta 2, initial state R2, and some collection of final states, accepting states F2. There exists a discrete automaton M2 such that M2 accepts the word W2 if and only if W2 is in the language B. And what we have to do is we must prove there exists, and in fact, what we shall do is we shall construct a finite automaton M, Q sigma delta, some R start initial state, and some final state, that accepts a word W if and only if W is in A or W is in B, or both. This is the same as saying W is in A union B. Okay. So this is a theorem we have to prove. If A and B are regular languages, then their union is a regular language. That means there exists some discrete finite automaton, some machine, that accepts a word if and only if it's in A or B, that if and only if it's in A union B. And we know that for A, there's a discrete finite automaton that accepts it, M1, and for B, there's a discrete finite automaton, M2, that accepts it. So somehow we want to construct a machine that somehow looks at a word and runs it through the machine, through the automaton, so like through M1 and M2 in parallel. So you take a word W and you plug it into the machine M1, and it goes through a sequence of states. And if it ends up in a state in F1, it's accepted. And that same word, if you plug it into M2, goes through a sequence of states, the same number because it's the same word. And it's accepted if it's in F2 and not accepted, it's rejected if it's not. So if that word in either of these two machines ends up in an accepting state for that machine, F1 for M1 and F2 for M2, then we know that then it's accepted, and we want to know the words that are accepted are exactly and nothing other than the words in A union B. So I want to try and figure out a way to have a machine that sort of goes through these two machines in parallel. And a very clever way to do this. So someone clever thought this up, and then everyone was happy and said, "Oh, okay. Now we know how to do it. Here's how we do it." So let's recall. We have machine one, which has states Q1, sigma, the alphabet, transition function, starting state, and some accepting states. In M2, that's another automaton. There's a set of states Q2, the same alphabet, a transition function delta 2, and a starting state, and some accepting states. So let's look at a machine Let's see. This is going to be the machine we're constructing. And suppose we let Q be what is called the Cartesian product, Q1 cross Q2. This means this is a set of all pairs, say R1, R2, where R1 is some state in Q1 and R2 is a state in Q2. Q1 and Q2 are finite sets. Every automaton has only a finite set of states. So you look at all possible ordered pairs where the first coordinate is a state in Q1 and the second coordinate is a state in Q2. So we have all of these states. And let's say, maybe this notation isn't so good. Maybe I'll call this R1 star and R2 star. They're the starting states. So if I take R1 star, R2 star, that's an ordered pair. And that's going to be the starting state, the initial state of this new machine, this new automaton we're constructing. And what is the transition function? Right? So we know the states. If you have two states, suppose you have R1, R2, and R1 prime, R2 prime. So these are ordered pairs. R1 is in Q1, R2 is in Q2, R1 prime is in Q1, R2 prime is in Q2. And I want to know, like coming out of R1, R2, where does it go? So suppose we have let's just make it easy. Suppose In both cases, sigma is just 0, 1. So we have to have an arrow coming out of R1, R2. If you're inputting the state 0, and another arrow coming out if you have 1. So what I want to let R1, R2 get mapped to, so this state, this ordered pair, has to get mapped to another ordered pair. Now, delta 1 of R1, 0 is a state in Q1. And delta 2 of R2, 0, that's a state in Q2. And this is what I call delta of R1, R2. So in this new machine I'm constructing, the state R1, R2 has to go to another state. It goes to the state delta of R1, R2, comma 0. If the input is 0, that's where it goes to. And if the input symbol is a 1, delta of R1, R2, comma 1 is going to be delta 1 of R1, 1, comma delta 2 of R2, 1. That is, we just let delta 1 act on R1 and we let delta 2 act on R2, and we get this ordered pair. So what is actually happening is you start with R1, R2 star. That's your starting state. And then where this goes to is where the first coordinate would go to in the machine M1 and where the second coordinate would go to in the machine M2. And we continue this. And if you look at the sequence of states as this automaton is running, the first coordinate is tracing what's happening in machine M1, and the second coordinate is what's happening in the machine M2. And when do you accept a word? When does this new machine accept a word? Well, it accepts the word W if W is neither A or B. That means your final state is going to be everything of the form any coordinate where the first coordinate's in F1 and the second coordinate is anything, or where the first state you're in is anything in Q1 and the second is an accepting state for the second machine. So as you're running the machine, if you end up in this finite set of states, it means either the first coordinate is in F1, so your machine M1 would accept the word, or the second coordinate is accepted by the machine M2, so your word is in the regular language for the machine M2. Okay. So this is a little bit complicated construction. And of course, it's described in the video lecture from MIT, and it's described in the textbook, and it's described here. So maybe the best thing to do to try to make this a tiny bit clearer is to actually write down this construction completely for two languages, A and B. So suppose we have a discrete finite automaton, M1, So for M1, the states Q1, let's say there are two states, call them Q1 and Q2. The language, the alphabet is just 0, 1. And let's say the initial state is Q1, that's the start. And the accepting state, there's just one of them, is Q2. And let's say the picture of M1 is the following. There are two states, Q1 and Q2. Q2 is the accepting state, so there are two arrows around it. Q1 is the starting state. Let's say that 0 sends Q1 to Q1, and 1 sends Q1 to Q2. Let's say that 0 sends Q2 to itself, and 1 sends Q2 back to Q1. So this is the automaton M1. What's the automaton M2? Let's say the automaton M2 has three states. I'll call them R1, R2, R3. It's the same language, binary symbols. And let's say that, so there's some transition function. Let's say it starts at R1, and let's say the one accepting state is R2. So that's the start. And these are the accepting states. And let's say that the diagram for M2 is as follows. We have R1, R2, R3. There are three states. An arrow out of nowhere into R1 means R1 is the start state. A double circle around R2 means R2 is an accepting state. And the alphabet is 0, 1, so I need two arrows coming out of each state labeled 0 and 1. So suppose 0 and 1 both send R1 to R2. Let's say 0 sends R2 to R3, and 1 sends R2 to R1. And for R3, let's say 0 sends R3 to R1, and 1 sends R3 to R2. So this is a finite automaton. So we have two of them. And what is the product? So in the product, what are the states? So Q is going to be Q1 times Q2, the product of these two sets. So there are two possibilities for the first coordinate, Q1 and Q2. So the possible states are Q1, R1, Q1, R2, Q1, R3. Or first coordinate could be Q2, Q2, R1, Q2, R2, Q2, R3. Those are all the states. And let's draw the state diagram for the machine we're constructing. So I have Q1, R1, Q1, R2, Q1, R3, Q2, R1, Q2, R2, Q2, R3. And the start state, if the start state here is Q1 and the start state here is R1, then Q1, R1 is going to be the start state. Okay. And now I need to construct the transition function. Oh, and what's the final state? So M1 accepts if the final state is Q2, M2 accepts if the final state is R2. So Q2, so what are the final states? So the final states for this new machine we're constructing, call it M1 cross M2, it's all pairs where either the first coordinate is Q2 or the second coordinate is R2. So there actually are a lot, in this example, a lot of final states. So anything that has a Q2 in it, that's the first coordinate, and anything that has an R2 has the second coordinate. So these four states are final states. If you end up in any one of these four states, then your word is an A union B, and if and only if. So what about Q1, R1? Suppose you have a 0. So 0 sends Q1 to Q1 and R1 to R1. Let me, so in the machine M1, Q1 goes to itself under 0, and R1 goes to R2 under 0. So that means that Q1, R1 in our machine is going to go to Q1, R2. So Q1, R1, so 0 sends Q1, R1 to Q1, R2. This is in M2. In the first machine, a 1 sends Q1 to Q2. In the second machine, a 1 sends R1 to R2. So in the product machine, Q1, R1 gets sent to Q2, R2. So Q1, R1 is sent by 1 to Q2, R2. What about Q1, R2? So Q1 under 0 goes somewhere, and R2 under 0 goes somewhere. Where do they go? In the first machine, Q1 under 0 goes to Q1. In the second machine, R2 under 0 goes to R3. So this means that the pair Q1, R2 gets mapped to Q1, R3 under 1. That's over here. Oh, sorry, what I said wasn't wrong. In our first machine, 1 sends Q1 to Q2. So 1 sends Q1 to Q2, and in the second machine, 1 sends R1 to R2. So Q1 R1 under 1 gets mapped to Q2 R2. Q2 R2, oh, well, that's I already calculated that. That's weird. Let me just double check all this. So I have our states, my M1 has 2 states, Q1 and Q2. M2 has 3 states, R1, R2, R3. So the Cartesian product is going to be a set consisting of 6 states. There's 6 pairs. First coordinates are Q1 or Q2. Second coordinates are R1, R2, or R3. So there's 6 states in this product. And here they are. And how do they get mapped? So under 0, Q1 goes to Q1, and R1 goes to R2. So Q1 R1 goes to, under 0 goes to Q1 R2. What about under 1? So 1 sends Q1 to Q2, and 1 sends R1 to R2. So under 1, Q1 R1 goes to R2 Q2, Q2 R2. Let's look at Q1 R2. Under 1, Q1 goes to Q2. Let's do 0 first. Under 0, Q1 goes to Q1, and R2 goes to R3. So this goes to Q1 R3. And under 1, Q1 goes to Q2, and R2 goes to R1. So this goes to Q2 R1. Under 1. And step by step, we can fill in all the arrows, that is, we are computing the transition function for this machine. And for this machine, the regular language is A union B. It's everything which is either every word that is accepted by M1 or every word accepted by M2. Right? That's how we construct the machine. And this proves that the set of regular languages is closed under the operation of taking unions. If A and B are regular languages, so is A union B. Okay. So in the next talk, I'm going to show that if A and B are regular languages, so is their concatenation. And if A is a regular language, so is an A star. But to do this, I have to introduce another form of finite automaton. The form we have is deterministic. So DFA, which is deterministic finite automaton. Deterministic means everything is determined. You have your set of states. You have your start state. And if you're in a given state, say you're in Q2, where do you go if the next letter in your word is a 0 or a 1? So that's determined. There is some arrow coming out of Q2 going to another state labeled with a 0 and another arrow labeled with a 1. So if you have some word 0, 0, 1, 1, whatever, everything is determined, right? If your first letter is a 0, then you have to take this arrow. If the first letter in the word is a 1, you take this arrow. Step by step, everything is determined, and you end up somewhere. If this is an accepting state, the word is accepted, otherwise the word is rejected. But everything is determined. There's no ambiguity or uncertainty at any point. But now we are going to consider something called an NFA. This is a non-deterministic finite automaton. It's going to have some start state, but it might have a diagram that looks like this. 0, 0, 1, 1, 0. Now, maybe a 1 here. Now, this is strange because in state Q1, suppose you get a 0. So where you go next, it's not determined. There are two possibilities because there are two 0 arrows coming out of Q1. So you could stay at Q1, you could go to Q2. If you get a 1, you have to go here. That's all it is, but yeah. Suppose you're in state Q2. If you get a 1, you can either go to Q1 or to Q3. But what happens if you get a 0? Well, you can't go anywhere because there's no arrow coming out of Q3 labeled 0. So you're blocked, you're dead, you stopped. You can't go any further. If you're in Q3 and you have a 0, you go to Q2, but there's no arrow labeled 1 coming out of Q3, so you can't go anywhere. So this is non-deterministic. Or you can think of it like this. Suppose you have the word 0011. So what happens when you input this word into the machine? So you start at Q1, and the first thing you have is a 0. Now with the 0, there are two places you can go. So think of this as you're creating kind of like a parallel computer. So on the one hand, you can stay at Q1, or you can go to Q2. Then you get another 0. From Q1, you can stay at Q1, or you can go to Q2. In Q2, there's no 0 coming out. So you're blocked. That's the end of it. Okay. The next letter is a 1. When you have a 1, from Q1, you can only go to Q3. When you have a 1 from Q2, you can also only go to Q3. In Q3, you get another 1, but there's no 1 coming out of Q3, so you're blocked. You don't go anywhere. That's it. You're not accepted. Everything is dead. It's kind of like a parallel processing thing. Anyway, we'll talk about that more in the next talk. Again, everything is discussed in the MIT lecture on YouTube, on the video, and it's also in the book. But this is really important because non-determinism is a big deal in mathematics and theoretical computer science. And that's it for today.